Hey, good morning, everyone. This is me, Celso Batalha, and these are some few problems in chapter 5. Um, so let's go through them. Start getting ready here. Okay. Um, so in the figure, we have a 10 pounds weight suspended from two spring scales, each of which has a negligible weight. Which one of the following statements about the readings? Okay. So think about these means, you know, being held by a string. So if you have a string and you have a 10 pounds weight pulling down, then certainly the string itself, assuming the weight is not moving, the string itself, excuse me, string itself is exerting an upward force 10 pounds. So according to Newton's law, the net of these two forces must be zero, right? Because it's not moving, the acceleration is zero. Um, so F is equal to 10, so we have a 10 pounds force along the string, and which means if you take the upper part of the string and replace by a scale, and the lower part by another scale, each one will read 10 pounds. So what are the, each scale read 5 pounds? No. The top scale, no. The lower scale, no. No. So E. Number two, two blocks A and B being pulled to the right along a horizontal surface by a horizontal 100 newtons force. As shown in the figure, both of them are moving together. Constant velocity, this is very important. So when you read this word, words, constant velocity, it means your system has an acceleration which is exactly 0.000 meters per square second. But the constant velocity is given 2 meters per second to the right, both weights are the same. Okay, so which of the figures below shows the correct free body diagram? FBD, the only free thing in physics. FBD, free body diagram of the horizontal forces acting on upper block A. Oops. Okay, if you take upper block A, let's do a complete free body diagram, not just um, a horizontal one. So if you think about block A has Earth pulling it down. So it has a weight, right? It has a weight. And this weight is given by its mass times g. But it also has the upward reaction of the block B on it. It's a normal force. You can call normal force that block B exert in block A. And since block A is not pulling up and jumping up and down like a popcorn, the magnitude of these two forces happen to be the same, right? The magnitude, the numbers that represent them should be the same. Now, and what else? What else is going on on block A? Now you might think, okay, so it's moving to the right. If it's moving to the right, then something must be pulling. But see, if this block moves to the right with a constant velocity, so velocity is constant, it means the net force on block A must be 0. So you might think, well, friction is being responsible for moving it along. But that's not true because there is no friction there. You have to have friction to initiate a motion. Let's say the block A or both blocks are not moving, and then you start moving block B. So then it is true you have to have some friction, hopefully static, that can initiate the motion of block A up to the point that it reaches 2 meters per second, and then you have a constant velocity. And when you get to that point, if you maintain that the velocity as being 2 meters per second, it means the net is 0. So once you initiate the motion, according to Newton's law, if no net force applies to the object, acceleration is 0. Since acceleration is 0, therefore there is no force to the right on block A. So answer is, I can't read what is written there, but it should be 0 force. And what is this? Two blocks, A and B, are being pulled to the right along a horizontal surface. The same thing, right? Which of the blocks below shows the correct free body diagram of the horizontal forces acting on block B? Oh, constant velocity. Okay. Now look at this. So if you take block B, let's do the only free thing in physics for block B. You have a free body diagram, which means let's initiate with its weight, which is mass times g. You also have the normal force the table exerts on block A. Table on block B, right? Table on block B. But look at this. You also have block A on top of it. So remember the force we identify up here? There is a reaction to that force on block B, which has same magnitude, opposite direction, which is, I'm going to call FA, F normal, A on B, F normal, A on B, this one. And then what else? Well, I do have 100 Newton. You have 100 Newton pull to the right. And if the constant velocity is assumed to be the case, you must have necessarily some friction force, right? From the table, this is friction force. And if it's moving, it has to be kinetic. Table on B. To the left, which must have the same value, so that they move with constant velocity. Okay. So there you go. B seems to be a good answer. Oh, I don't like this. Look at this. Oh, my lower back. Oh, God. Oh, God. That's no good. Those of you doing biothing, tell your clients not to do these things. That's such a bad posture. So I show in the figure a woman straining to lift a large crate, but without success because it's too heavy. We denote the forces on the crate as follows. P is the magnitude of the upward force being exerted on the crater by the person. So let's take the crater out. So here's the crate. And let's indicate the forces on it. So you have P is the magnitude of upward force on the crate by the person on P, person on the crate. C is the magnitude of the vertical force on the crate by the floor. So you also have a normal force here. right? That's the normal force, floor on person. This on is very important because when we do a free body diagram on something, you have to identify the forces that the universe do on that thing. Okay? And weight is the weight of the crate. So, and weight is a force that arises because Mother Nature. So let's keep. So weight is a force that arises because Mother Nature, Earth, is pulling it down. Okay. How are the magnitude of this force related while the person is trying unsuccessfully, which means the crate is not being lifted. If it's not being lifted, it means the weight is bigger than these two forces. Wait a second, I forgot to write a C. P is the magnitude of get on the crate, but C is the magnitude of the vertical. Oh, C. This is called C, right? This is C. So, oh, wait a second. Oh, yeah. So I kind of did it wrong. Um, it's not being lifted. The crate's not breaking the floor, which means these two values here are the same. Wait a second. Let me erase this. There you go. Oops, wrong. There you go. These two quantities must be the same. I mean, she might increase p to the point that eventually it's going to be bigger than the weight and then she can lift, right? Or she's going to break her lower back. But as long as the crate does not break through the floor, um, the weight is um, the weight is being able to match these two forces. Again, the crate is not moving, which means the acceleration of the crate upward or downward acceleration is zero, which means the net of these two forces or three forces must be zero, which means P plus C minus W. This is the net, must be equal to zero. Then the options go, yeah, A should be the good one. A push of magnitude P acts on a box of weight W. Let me write the free body diagram quickly. So we have a weight, we have a normal force, Fn, which is exerted by the floor on the crate, and we have this downward P. See, I'm just taking this force P and I'm outlining here, so it's easy for me to see what's going on. And there is an angle theta right here. So I took it out of here, basically. The push is directed at an angle theta below the horizontal, angle theta below the horizontal right here, and the box remains at rest. Oops. So if it remains at rest, the box, it has to have a friction, right? And which means there is a friction like this, and it has to be static. And the reason is the block is not moving, rests, it's not moving. The normal force on the box due to the floor is equal to what? Okay, let's figure. The normal force can be derived if you think about your axis, the Cartesian axis. Let's call these directions to the right and upward as being the positive direction. So all vectors that happen to be aligned along these directions will carry a positive sign. So If that is true, the static friction has a positive sign, right? Has a positive sign. And which other forces happen to project itself along the x-axis, P? So if you take P and project along x-axis, this is what you got. You got something which is equal to P cosine of theta. How do you get cosine and sine? Or should I use tangent? You always get that confused question. Think about adjacent. Cosine is given by the ratio between the adjacent part of a triangle, it's right here, and the hypotenuse. So you should use cosine. So minus P cosine theta. Since it's not moving, this is equal 0. If it were moving to the left, you would write mass times acceleration, basically. Okay, like Newton's second law. So this is the equation derived when you look at x direction. Now, when you look at y direction, what you got? Well, what you got is positive normal force. Now, which force projected itself along the y direction? Well, P does, but not this friction force. The friction force projects nothing, right? Projects a dot. So there is no projection of static friction along the y direction, but the weight does. So we have weight. Oops, sorry. Sorry, where's my eraser? No, this is not eraser. There you go. Oops. That's my eraser. So see the weight is pulling down, right? The weight is pulling down, so it has a negative value. But also the projection of P along the y direction. See the vector here that goes downward? So essentially what we did, we took P out of the picture and then we replaced vector P by its projection, negative P cosine theta and negative P sine theta. So minus P sine theta. So the normal force, we want to find normal force. The normal force, and this is equal to 0 because the block's not jumping up and down. So the normal force is equal to W plus P sine theta. So this is a good one. Two boxes P and Q on a perfectly smooth. What does it mean, smooth? It means frictions are not an issue here, right? There's no friction. Are connected by a light horizontal cord. The mass P is greater than that of Q, so which means the weight of P is greater than the weight of Q. And you have a horizontal force F applied to box Q, showing the figure, accelerates the bodies. Oh, so you have acceleration to the right, which is okay because you don't have friction. The magnitude of the force exerted by the connecting cord on body P. So let's take a free body diagram of block P. What are the forces acting on P? I do have its weight. I do have its weight. And I do have its normal force. P. And since there are no friction, I don't need to worry about friction, but I do have a tension cord. And the problem wanted me to say something about this tension force, the magnitude of the force exerted by the connecting cord on body P. But that's it. I don't, I mean, it can't be 0, right? It can't be 0. Because, why is that? Well, because this block P is moving to the right with a certain acceleration, right? It is accelerating. So I know that T, this tension T, must be equal to the mass of block B times acceleration. This is what I know. So, but see, the other possible options refer to F. So then I have to figure that out. I have to somehow relate or find a connection to relate T with F. How am I going to do that? I have to get block Q. Here's a block Q. If I do a free body diagram on it, to the right I have F, right? Now to the left, do I have any impeding force acting on Q to the left horizontally? The answer is yes. I would have friction, but the surface is smooth, so I don't need to worry about it. But I do have a tension, and the tension is a force that has the magnitude the same as this force. I mean, it is a pair action reaction. In fact, the two tensions are not the same. I mean, we call the same symbol, which is not correct exactly because the vectors are not the same. The magnitude is, so the number, the amount of newtons representing is the same. We do have also a normal force, and we do have its weight, right? We do have its weight. But when we think about the x direction only, now what we can write, assuming there is an acceleration on block Q, is that F minus T is equal to MQ times A, the mass of block Q times acceleration. This is what I know, right? And I want to find a way to relate T with F, and then I can do that if I switch around here, and then I find that tension is equal F minus something, which means tension is less than F. So which one? Tension is less than 0. No, less than F, but not 0. Yeah, that looks good. Tension can't be 0 because you have an acceleration that is not 0. So B is good. Oh, we did this in class. This is important. I mean, you should finish Physics 2A knowing how to solve this situation here. You have two boxes connect each other by string. Showing the figure, you have a 10 newtons box, slides without friction, so no friction. On the horizontal table surface, the pulley is ideal and the string has negligible mass. What is true about the tension in the string? So if this pulley has no mass, this tension that goes along this cord has a fixed value, okay? And I don't, can I read this? Oh, wait a second. Oh, it's 30. So you have 30 newtons mass in there, and then I can think about block 10 newton, right? When I do a free body diagram on it, Newton means weight. I do have 10 newtons pulling down. Attention, you all, newtons not mass. Let's say I could give you this problem not with the weight given, but mass. So, or in this case, if you need the mass, you have to be able to extract from the weight. So what's the ratio between those two quantities? So the weight is equal to the mass of this block times G. So the mass of, I call this block A and block B just to make it simple. So the mass of block A is equal to 10 divided by 9.8 kilograms. So this is in kilograms. By the same token, mass of block B is equal to its weight divided by 9.8, and then we have that in kilograms. Okay, so we want to find the tension. So I do have the weight, I do have the normal force of table on block A, and I do have a tension force, but that's it, right? I have a tension, and I don't know anything about friction. I mean, no, in fact, I know there is no friction. So, which means I do have an acceleration here, unless the blocks are not moving. But the block should be moving because B is 30 newtons. See that? So if I take the 30 newtons block and I organize the forces on it, I have a tension force upward. But see, the tension force has a magnitude which is equal to this tension force. The number is the same because the pulley is massless. And I do have its weight down here, 30 newtons. And this block falls down with a certain acceleration, which means 30, when I do the Newton's law, let me call this direction positive. So I deal with positive numbers here. I like that. 30 minus t is negative because it's a force that is pointing the direction that I'm calling negative, right? So anything upward here is negative. So t 30 minus t is equal mass of that block, 30 divided by 9.8 kilograms times the acceleration. So I find acceleration. See, acceleration should be a positive number. So then what I find is that, so I have two, basically, one equation here that relates tension, which I want to find, and acceleration that I don't need to find, but I don't know which one it is. But I also know that T, the tension from the 10 newtons block, is equal to its mass, right? Newton's second law times acceleration. So what I can do now is solve a system of two equations and two unknowns, tension and acceleration, and then I should be able to resolve this problem. Okay, so what I do, I can take acceleration out of this box. So acceleration is 9.8 times t divided by 10, right? So take acceleration here, plug it in there, and cross my fingers. Now, and then I have one system of one equation and one unknown, which is t, and then I can figure that. Oh, but yeah, I don't know. Yeah, here is only. So you could find a solution directly from 30 minus 30 times 9.8a, and 30 is, yeah, so you could see from here, since a is a positive number, that tension would be less than 30. And but you could calculate, and you would find a number if you solve the system of two equations and two unknowns in t and a. You would find t, and you would find a number less than 30. But somehow they don't want you to calculate here. Say, you don't need it. How about this? 30 kilograms load is being held in place using massless wires in the ideal pulley arrangement shown in the figure. What's the magnitude of force F? Okay, that is interesting. So you have a force F that is applied to a cord. So we have a cord here, right? And the cord is the same. That goes in here, up there, down here, and up here. So the wires are massless, and the pulleys are ideal. This is a key word to say the tension along this string or cord is the same. So you have a T all over. So if you take this part of the system here out, here's the pulley, you have a mass which is 30 kilograms. So the weight is 30 kilograms times 9.8, right? 9.8 meters per square second. Now, you do have an upward T and an upward T over there, right? And it's held in place, so it's not moving, meaning the acceleration is zero. There is no acceleration, right? It's held in place, it's not moving. So if you look at this system here, what you conclude is that 2t, t plus t is equal to t minus 30 is equal mass times acceleration, which is 0. T is equal 15 newtons. 15 newtons. Oh, what am I saying? 30 times 9.8, I forgot. So 15, wait a second. So T is equal, yeah, let's not be so massive. So T is equal to 30 times 9.8 divided by 2 newtons. Then you should find something that is a little bit less than 150 newtons. Let's just move around. What is this? 3 kilograms and that's 5 kilograms blocks rest side by side on a smooth level. Okay, let's make a level. So one block and another one. Okay, so let's make this the 5 kilograms block, although smaller, and a 3 kilograms block. Let's say this is a metal, this is a wooden box. 3 kilograms, 5 kilograms, side by side, and then smooth. So think about smooth means friction. Don't have friction. Horizontal force, 32 newtons applied to the 5 kilograms. 32 newtons applied to 5 kilograms block. Push against the 3 kilograms block, and as a result, both blocks slide along the floor. How hard the two boxes push against each other? So you want to find the force that arises between these two blocks. It doesn't say anything about acceleration. Let's see. So let's do the free body diagram on the 5 kilograms block. We have a 32 newtons force to the side, and you do have a reacted force on the 3 kilograms block on it. It's kind of a normal force if you think. So this is a normal force, 3 on 5, okay? And there is no friction, so that's it. You do have also the weight, 5 times 9.8 newtons, and you have a normal force, but they will not help anyway. This is stable on 5 kilograms, but they will not help. These vertical forces will not help in the movement. So basically the 32 minus this force, which is 3 on 5, is equal to its mass times acceleration. Okay, so we got that thing. Cool. Now, I can't answer the question because I don't know acceleration, and I don't know the force the block 3 exert on block 5. So what I do next, I go to the other block. So when I look at the 3 kilograms block and I try to single out the forces on it, so which forces do I have? I have a force which is a normal force 5 on 3. 5 on 3. Now, what's interesting about this force 5 on 3 is that it has the same magnitude, the same numerical value as the force that the block 3 exert on 5. This is Newton's third law. In addition to, the weight and the normal, but they don't help in the movement of this block, 3 kilograms block along the horizontal direction. And when I write Newton's second law of motion, what I find is this force 5 on 3 is equal to the mass of the 3 kilograms block times acceleration. Oh, how cool that is. Now I can take this quantity here and sub it in there. See that? And when I do this, 32 minus 3a is equal 508. Why did I do that? Well, I did that because the magnitude, the numerical value of these two forces are the same. And then I can sub it in there. And then from this equation, I find the acceleration is equal 4 meters per square second, and then I can find the value of what do I need to find? Oh, then I can find the force in which they push one another, which is 3 times 4, 12. Let's see one more. Just a second. Okay. So you have a 55 kilograms block that rests on a horizontal surface. Oops, wrong. Coefficient of static friction between the box. Oh, what happened here? Oh, I think I cut that one. Sorry. So I don't know if this is a driver in a 1,000 kilograms car traveling 25 meters per second. So we have a car moving 24 meters per second. Excuse me. Slams the brakes and skids to a stop, so eventually stops. Excuse me. 0 meters per second. So if you assume the decelerating occur excuse me. If you assume this deceleration goes on a uniform way, so you have a final velocity the initial velocity, and then you can find information, right? If the coefficient of friction is 0.8, how long will the skid marks be? So we want to find del x. So we can use Bernoulli for that, right? Final velocity square initial velocity square plus 2 acceleration excuse me, del x. We have final velocity, we have initial, but and we want to find this, we don't have acceleration. When you do the free body diagram on the car, weight normal, and the friction force, which is kinetic, that's the only there is. So that the friction force, which according to the Newton's second law along the x direction, is given by mass times acceleration. And the Newton friction force is equal to a coefficient of kinetic times the normal. I'm sorry, I'm having allergies or something. And normal force in this case matches mg. So that you can find acceleration from here. So acceleration is equal mk mg divided by m, which is whatever coefficient of kinetic you got, 0.8 times 9.8. So we have the acceleration, and with acceleration you can plug it in there, and then we can have the how long the decelerating process occur. Okay. Two packages are connected by a very light strings that goes over an ideal pulley as shown in the figure. Package A has mass 3 kilograms. Looks like problems we did in the lab, huh? And can slide along a rough plane inclined 30 degrees. above horizontal. The string acts on the package parallel to the surface of the plane. The coefficient of static friction is 0.4. This is static. What minimum mass should package B have, this one, in order to start package A is slipping up the ramp? So minimal, if it's more than that, it's gonna go accelerating, which requires to know the kinetic friction. But you wanted the minimal, is the one that will initiate motion. So basically, when you do free body diagram on block A, you do have the weight, MAG. I will only indicate the force since we did this type of exercise in the lab a lot. You have the normal force, in this case tension, and you have the static friction. Now the maximum value of static friction is coefficient of static friction. This is true for the maximum value, for remember that, right? Times normal force. But normal force is what? It's not mg. How do we know normal force? We can take gravity and replace gravity by its projection. And the projections are mg cosine theta. This is 30. And have another one here. Mg sine theta. So when you do your, so this is about to start moving, right? And T, therefore, is equal to the sum of these two forces. Sine of 30. And, but what is normal force? Normal force is equal to mg cosine theta, as you can see from the diagram. And then we can this is m block of mass A, right? Block of mass A, block of mass A. And now we can go to block B and see what's going on. So when you think about block B, block B has its weight and has the tension. And since this is about to move, but it's not moving yet, the acceleration is none, so mbg is equal to tension. But tension is this number here. So then we can say mbg is equal to 0.4 times Fn, which is mag cosine 30, plus mag sine of 30. So then we can find mbg if we divide everyone by g. So g can just cancel out. Okay. Okay. So that's it.